I now call to order the Society's 2514th meeting in what is now the 154th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., dedicated to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW meeting and the lecture by Jamie Bock. First, the Society is grateful to PSW Full Year Series sponsors, PSW member Mike Helton and Helton Associates LLC. Thank you, Mike. And to the Spring Series sponsor, PSW member Joe Schulman. Thank you, Joe. And to the sponsor of tonight's lecture, PSW member Martin Harwood. Thank you, Martin. The Society needs your support to meet its expenses for the year. All of this is not free. So if you've not given or you feel you can give more than you already have, please do not hesitate to donate. And if you would like to sponsor a lecture, please see me or Executive Director Robin Taylor at the back of the room. I am pleased to announce the following new members. Christopher Drennan, a periodontist and software developer interested in dentistry and medicine, computer sciences, robotics and AI, and astronomy. He's here in the audience, so please welcome Christopher. Anna Maria Cabell, a pediatric dentist interested in dentistry and stem cell research, who learned at PSW while at another event at the Cosmos Club, as did Christopher. So please welcome Anna Maria. She's here in the audience too. Jeffrey Murray, a physician and scientist, formerly Deputy Director for Family Health at the Gates Foundation, interested in neonatology, genomics, and global health matters, who learned a PSW from his son, who is a PSW member. Maya Ormsby, executive coach and educator with Aptive Resources, interested in psychology, genetics, and AI, who learned a PSW from a friend. Pramukta Rao, CTO at Zephyr, interested in geographic sciences, remote sensing, satellite engineering, computer vision, robotics, and statistical physics, who previously was a student member of PSW when he was studying for his doctorate, having joined after learning a PSW from former recording secretary Justin Steinmetz. Sasha LaFleur, founder and CEO of Yellow Bridge Partners. Think Pittsburgh, of its many yellow bridges. Interested in geology and earth sciences, who learned a PSW from PSW member Matthew Henry and from attending the PSW lecture on April 4. Peter Fellows, film and video producer and CEO of Juicebox Design Communications. Broadly interested in scientific discoveries, especially particle physics, cosmology, and astronomy, who learned a PSW from searching the internet. And tonight's speaker, Jamie Bock, who learned a PSW from our invitation to him to speak here tonight, and whose interests will be clear in part from his lecture. Please join me in welcoming them all to membership. All members are entitled to a signed copy of Volume 17 of the Bulletin of the Philosophical Society of Washington, aka PSW Science. And if you haven't received yours and you're a new member, please come and see me after the meeting. If you're interested in membership, you can access a membership application on the PSW website by clicking on the Join blue button on the home page at the upper right-hand corner. And if you're here in the Powell Auditorium, you can access the application form using the QR codes on the business cards on the tables at the back of the room. If you have any questions, please see me or Executive Director Robin Taylor or our recording secretary, Scott, or any of the other members of the General Committee here. We'd be happy to answer your questions. The requirements are you have to have won a Nobel Prize. I keep mine at home on the, yeah. No, you must have a genuine interest in science and be willing to pay the $75 fee after filling out the application. All are welcome. Recording Secretary Scott Matthews will now present the minutes of the 2513th meeting and the lecture by Josh Semitar on UAPs from sensationalism to science. Scott.
Thank you, Larry. Good evening. On April 4th, 2025, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2513th meeting of the Society to order at 8:03 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included the lecture by David Bennett titled Detecting Exoplanets by Gravitational Microlensing, Surveys, Gaps, and Rogues. The minutes were approved pending 2 minor corrections. President Milstein then introduced the speaker for the evening, Joshua Semitar of Boston University. His lecture was titled Unidentified Anomalous Phenomenon, From Sensationalism to Science. The speaker began by saying, quote, when you point sensors of ever greater resolution at the world, you see new physics, and it is not incremental, end quote. He went on to say, quote, it is absolutely perilous to translate your biases and experience from the visible into the infrared. Semitar showed several examples of digital images, both visible and infrared, that appear to be something very different from what they actually are. What appears to be a lampshade is actually a rolling disc. What appears to be 2 pieces of silverware is actually 3 pieces of silverware at different temperatures. The speaker discussed the 2022 NASA panel to investigate UAPs. He described the makeup of the 16-member panel, which included data scientists, physicists, representatives from the FAA and DoD, a science writer, and an astronaut. Semitar discussed the change in terminology from UFO to UAP, describing the stigma and the provenance associated with the UFO acronym. He described the mission and the major findings of the panel. These findings included the need for better data, the need for a disciplined scientific approach, the need to remove stigma around reporting, and the need for transparency between government agencies. The speaker presented the idea of technical surprise, the idea that clandestine technologies being developed by our adversaries may appear to be anomalous. Semitar then presented what he called, quote, the rules for the infrared. These included an aura is an artifact of standard contrast enhancement. An IR image does not represent the size or shape of the actual object. Objects can appear or disappear in IR imaging depending on their temperature compared to the background. And finally, the apparent motion of an object is affected by the motion of the observer due to parallax. The speaker showed a number of videos demonstrating each of these effects. Semitar then showed several videos of popular examples of UAP events, many which have been interpreted as evidence for extraterrestrials, anti-gravity technology, transmedium vehicles, and exhaustless propulsion. He began with the so-called Puerto Rico UAP event, which he concluded was, quote, 2 birds, definitely 2 birds, end quote. He then showed the, quote, Go Fast event recorded by pilots from the USS Theodore Roosevelt. By analyzing the range and elevation data recorded in the video, he was able to estimate the actual airspeed of the object. He concluded that the object was actually moving between 0 and 120 miles per hour, depending on the bank radius of the observing aircraft, and that the most probable velocity was between 35 and 40 miles per hour. Switching from the infrared to night vision, the speaker showed videos of flashing green triangles, also purported to be extraterrestrial in origin. He showed how the bokeh effect causes the image of a point source to reproduce the shape of the camera aperture when slightly out of focus. SPHEREx showed that the mechanical aperture in the night vision camera used to record the video was triangular and was in fact the exact same shape as the flashing triangle. Returning to the infrared, SPHEREx showed video of the so-called gimbal event, which some people claims to show a vehicle with a distinct shape or structure, an exhaustless propulsion system, and an aura surrounding the vehicle, with the vehicle rotating in a way that is aerodynamically impossible. He then showed videos of the way in which glare, recorded by a digital camera, rotates with the camera, not the object being recorded. He presented a plausible and quite convincing argument that the apparent shape of the object was due to IR glare and that the object never actually rotated. The imaging system rotated. The speaker ended his talk by listing some of the recommendations of the NASA UAP panel. These included creating a dedicated NASA point of contact, establishing baseline data for sensors used to record such events, and enlisting citizen scientists or crowdsourcing. Finally, he said, quote, "There is so much wonder in the universe that stems from real physics. We do not need to make up explanations to keep things exciting," end quote. The lecture was followed by a question and answer session. A member asked if there are other events or anomalies that still appear to defy explanation. SPHEREx responded, quote, "Yeah, there definitely are," end quote. He described a number of these events, noting that the lack of explanation may be related to incomplete data. A member asked whether the pervasive use of digital cameras could result in imaging anomalies or artifacts not associated with analog or film-based imaging techniques. SPHEREx responded that for the most part, digital cameras do behave like wet film. However, things like pixel blooming and hot pixels are unique to digital cameras, and these artifacts need to be recognized and understood. He said that the advantage of digital imaging far outweighs the disadvantages. A guest on the live stream asked if UAP events might provide useful information about unusual or elusive phenomena, even if they do not provide information about extraterrestrials. SPHEREx responded, quote, "Absolutely. That's why we call this stuff anomalous phenomenon, because we'll take anything," end quote. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. He adjourned the 2513th meeting of the Society at 9:33 p.m. Eastern Time. Temperature in Washington, D.C., 20 degrees Celsius. Weather, cloudy. Audience in the Powell Auditorium, 96. Viewers on the live stream, 38. For a total of 134 viewers. Views of the video in the first 2 weeks, 134. Respectfully submitted, Scott Matthews, Recording Secretary.
We now turn to tonight's lecture by Jamie Bock. Jamie is an experimental cosmologist and the principal investigator of the SPHEREx mission. SPHEREx stands for Spectro-Photometer for the History of the Universe, Epoch of Reionization, and ISIS Explorer. His research is focused on pioneering new technologies and instruments designed for fundamental measurements of the state of the universe. Prior to SPHEREx, he developed wide-field telescopes and superconducting bolometer arrays that enabled the bicep Keck observations that place constraints on cosmic inflation. He also led the development of the focal plane detectors on the Planck and Herschel satellites, which built on his graduate work on the Boomerang CMB project, which itself provided initial evidence that the universe has a flat geometry. Much of his work has informed the design of SPHEREx, which will precisely measure galaxy spectra and redshifts, discern patterns in the intra-halo light and from the Epoch of Reionization, and explore the driving forces of early universe inflation. He is an author on over 800 scientific papers, mainly focused on technology, astronomy, and cosmology. Among other honors and awards, he received the Gruber Cosmology Prize as a member of the Planck team, the AAS Weber Award for Astronomical Instrumentation, and the SPIE Goddard Award. Jamie earned a BS in Physics and Mathematics at Duke, for which corresponding Secretary Robin Taylor, a Michael Jordan-era UNC grad, will forgive him, and a PhD in physics at UC Berkeley. All questions will be fielded after the lecture during the question and answer session. All your questions will be answered then, so be patient. Jamie, the stage is yours.
Okay, thank you very much. I'm new to PSW, and so I'm delighted to find this wonderful organization. I'd like to thank Martin Harwitt for sponsoring this talk. Thank you, Martin. And I would like to say that at Duke, we call that the Johnny Dawkins era, not the Michael Jordan era. So the timing of this talk is interesting because the project I'm going to tell you about, SPHEREx, launched on the 11th of March. So instead of the usual talk, I'm calling it SPHEREx First Light. And there will be a few intriguing glimpses of first images from SPHEREx at the end. SPHEREx is a satellite that's designed to explore fundamental questions about astrophysics and cosmology. And you can see them there. What's the origin of the universe? How did galaxies form and evolve? And what's the origin of water that's so important to life here on Earth in our galaxy? And while it's doing this, it's going to make a new data product, which is the first all-sky spectral survey of the entire sky. I'll tell you a little bit about the unique design of SPHEREx and then some of the good stuff here. And you can see from this picture our deployment right after launch. So we've been observing now and tuning up the instrument in preparation for science observations to come very soon. I would like to say that SPHEREx is a type of satellite called an explorer satellite. And these are missions in NASA that are competed to do PI level science. So you choose the science, you go through a fairly brutal competition and selection, but then if you are selected, you get to go ahead and implement the science involved. Currently, they come in two flavors, small and medium. There's a large flavor coming in astrophysics. And they have a long and storied history here for doing, I think, very important measurements in astronomy. But the key thing is that they're resource capped. So when you come up with a concept, it has to fit in a multi-dimensional resource constrained box, mass, volume, but also explicitly cost. So it's always important. Everything we do with SPHEREx is in a cost. Cost is always part of that equation. And it's an interesting way to do science, but I think the track record here for these kinds of missions is really quite excellent. Caltech, where I'm from, has also had quite a track record here. So some of these missions are Caltech missions, including New Star, which is X-ray, gamma ray experiment. Then SPHEREx, also Galax here, another small explorer, was a Caltech mission. And then just recently, the selection of UVEX, which is a coming ultraviolet medium explorer. So you can see the numbers. The latest cost cap for MIDEX is about $300 million. And so that sounds like a lot of money, and it is, but it's mid-sized for a space program. Okay, so here's a little video that shows a simulation, obviously, of SPHEREx before it was launched. And you can see a couple of things. First of all, we have this very distinctive cone shapes up at the top. We're obviously in low Earth orbit. And if you were noticing, we're going over the sunrise-sunset line, which is necessary because SPHEREx is an infrared observatory. And so in the infrared, we're very sensitive to heat. And so we need to cool our telescope and detectors to low temperatures. This is a challenge in low Earth orbit because we have the sun on one side, and then we have the Earth at about 300 degrees Kelvin subtending 2 pi steradians below us. So you saw those cone shapes, and that's integral to our cooling design. Basically, we use a method of cooling that doesn't use stored cryogens or a mechanical cooler. It's entirely passive. So we radiate heat out to space and use the coldness of space to do that cooling function. And we've taken this to extreme levels. This is really aggressive passive cooling, or as some say, passive aggressive cooling. So the heat radiates out to stages in multiple stages, and the telescope and the detectors are cooled to very low temperatures. So it's quite an engineering feat to do that in low Earth orbit. The other key part of SPHEREx is the telescope. It's a modest telescope. It's only a 20 centimeter aperture, and you can see here the entrance aperture of the telescope. But in spite of its small size, it's very powerful because it collects a huge amount of light, and that's reflected in having a very large field of view on the sky. So in spite of the small aperture, the product that's of interest for mapping is the product of the area and the solid angle. Area of the mirror is expensive because you have to have a bigger and bigger telescope, and we know that's costly, but field of view is kind of cheaper. And so that's the trick we use to get this mapping speed power with SPHEREx. Finally, we are sitting on top, this telescope is sitting on top of an agile spacecraft. And so this spacecraft provides power, commanding, data, and points and directs our observations. So here's a cross-section view of SPHEREx, and you can again see the telescope, the large field of view. It's about 40 square degrees. Cooling of the telescope and the detectors. I can say now that the telescope has been cooled to 62 degrees Kelvin, 62 degrees above absolute zero, and the detectors are sitting at 45 degrees Kelvin. That's quite an achievement, I have to say, in low Earth orbit, and really a tribute to our excellent design team. The telescope has got 3 mirrors, but it has this wide field of view. You can see the light bouncing in the aperture. And then finally, the way we do spectroscopy is very novel here. We actually take a filter and sit it right on top of the detectors. And that filter, the passband of that filter just varies continuously as you move along the filter. So each position on the detector is viewing a bit of a different wavelength as a result. And so that's a very compact, efficient way to do spectroscopy. These filters are just pieces of sapphire about that big. Very compact, especially when we initially looked at designs of more conventional spectrometers. We would have something like 6 of them, and each of them would be the size of the telescope. So that wasn't going to work. And so we came up with this novel idea. Turns out it's not novel. Planetary science has been doing this for a while, but in astronomy, not so much, because you really want to put all your pixels on the target and not waste them looking off the target. And so that bias took a while to overcome until we realized that our target here is really the full sky, and having all those pixels everywhere is just perfectly fine. We do this spectroscopy in these different channels where the filters are placed over the detectors, and it's called low resolution spectroscopy. So we have resolving power here, if you do spectroscopy, between about 35 and 130. So not super high resolution spectroscopy, but enough to do our science. Okay, so here's how the filters work. As I said, every observation gives you the wavelength where that source lands on the detectors. So each of these data points is actually an exposure where we sit there and we stare at the sky for about 2 minutes and we get that point. For the source that's going by here, we measure that source at that wavelength, but other sources are measured at other wavelengths, depending where they land on the detectors. To get a complete spectrum, we have to take 51 exposures. We see the source in 2 bands at once, so we get 102 colors combined. And after those 51 exposures, we have a complete spectrum. And so this is obtained by taking a series of pictures, and nothing in the instrument moves, and we use the spacecraft to orient the telescope to take those exposures about 2 minutes each. Now, this kind of makes a giant jigsaw puzzle, as you can imagine. So each of these pieces of sky is observed at different wavelengths, and so we have to have an observing strategy where we can put it all together and then measure the spectrum of everything on the sky. Okay, so this video kind of shows how that works. Again, we're an infrared telescope, so we can't look towards the sun, and we can't tip too far down, or we'll see the emission of the warm Earth. And so that leaves a sort of semicircular region where we can point the telescope at any given moment. And so this video here is showing how that works, and it's sped up. So each of these exposures is about 2 minutes. So we take a series of small steps, an exposure, get a picture, step, take another exposure. And as we're doing this, we're orbiting the Earth. And while we love the Earth, it does sort of get in our way. And so every so often, we have to do a big slew to kind of reset that observing sequence again. And then we do these small steps. And while we're doing that, we're pretty much looking about 90 degrees from the sun. So as you can imagine, as we take these exposures going around the Earth, we're kind of doing these observations in a great circle that is going around the sunrise-sunset line 90 degrees from the sun. And so very greatly sped up, this is how that process works. The initial survey that I was showing, this is now whizzing by, time's whizzing by. You can see each of these exposures would be about 2 minutes, 98 minutes for the orbit. But that great circle of observations, it rotates as the Earth goes around the sun. And as time goes by, that circle rotates, and after 6 months, it closes. And so in 6 months, we have full sky coverage, as you see here. And so we actually have an independent map, multiple ones over our mission. Our baseline mission's 2 years. So in 2 years, we get 4 independent, all-sky, complete spectra of every pixel on the sky. Okay, so let's talk a little bit about the science. And we'll start closer in and work our way back and further away. So the science questions, I think they're very profound. Where's the water in our galaxy? How did galaxies begin, form, and evolve? And how did the universe begin? So let's look at the first of these. Where's the water in our galaxy? On Earth, we know that water is essential to life on Earth. We have one data point, though, life on Earth. But everywhere there's liquid water, we see life. I work sometimes at the South Pole. At the South Pole, on the polar plateau, there's no liquid water and there's no visible signs of life, except other scientists. And so where did that water come from? And we believe that the water on Earth actually had an interstellar origin. So that water formed in interstellar chemistry, and in the process of the solar system and the sun being born, somehow that water got into the inner solar system. And the interesting thing is that water is not in the form of vapor or liquid. In the regions where stars form, water is actually out there in the form of ices. And those ices form through very slow interstellar chemistry on the surfaces of interstellar dust grains. And so these icy reservoirs are the basis for water on Earth today. And how can we learn more about them? So these measurements have been done to some extent in infrared astronomy, but not systematically. And basically the idea is we can look for the fingerprints of ices through a technique called absorption spectroscopy. So basically we put a star behind the object that we look, well, we don't put it there, it happens to be there, and we use that to explore the properties of the cloud. And water and, as it turns out, other ices have distinctive absorption features. And these other ices are interesting as well. So you can see the very broad absorption effect from water ice, but also absorption features from carbon dioxide, carbon monoxide, and methanol. And this measurement tells us the abundance, the column of those materials. And while this has been done in hundreds of objects to date in astronomy, let's do this systematically. And so let's map the abundance of these water and organic ices over the entire sky. And we can do this going from the early stages of star and planet formation, so through the clouds where stars and planets are born, to when they're turning on and forming interplanetary disks, and look at this evolution of these important constituents. And we can predict how many objects we expect to see because we have certain rules. We want to have a star that's bright, and we want it to have it behind a cloud, and we want it to be fairly isolated. So in advance from other data sets, we can make a target list of all the objects that we can do high-quality measurements of the abundance. And this is the map. It was made prior to SPHEREx, and it's, I think, super impressive. There's almost 10 million targets on this list. You can see they're concentrated in the plane of the galaxy, but this is just an unprecedented survey of these important materials. So moving along to our next theme, how do galaxies begin? And you might think with SPHEREx that this is something we're not going to do very well, because we're a small telescope, and everyone's building these increasingly giant telescopes to look at objects further and further and further away. We have the James Webb Space Telescope. We have plans for even larger telescopes on the ground. How are we going to do something with our dinky little 20-centimeter telescope? And so we're doing something that's very different. And the idea is, this is a history of the cartoon history of the birth of the universe. So we believe the universe started in a hot Big Bang about 14 billion years ago. The universe was originally hot and dense. As the universe expanded, that cooled off. We have this fossil relic called the cosmic microwave background from a very early time when the universe was a mere 380,000 years old. From when the hydrogen formed in the universe. So prior to the CMB, cosmic microwave background, there are free electrons and protons, and then when those electrons combined with protons and formed hydrogen, suddenly the universe became transparent. And so that microwave background is the photons that come from that time when the universe went through this period of becoming transparent. At that time, the universe consisted mostly of hydrogen and helium. And through a process that we don't really understand, the first stars and galaxies formed several 100 million years after the Big Bang. And so that period of time is called the Epoch of Reionization, because those stars and galaxies, the bright light from them ionized all the gas around them. And the universe today is almost perfectly ionized. So we'd like to learn more about it. That phase, it's an active area of study. But after those first stars and galaxies, star formation continued apace and rapidly increased. That period of Epoch of Reionization is also called cosmic dawn, because that's when galaxies and stars turned on. There's another period called cosmic noon, about 5 billion years after the Big Bang, when star formation kind of maxed out in galaxies. And actually, since this time, it's been on a slow decrease. So how can we study this kind of grand picture with SPHEREx? And so what we're doing is we're not studying the individual objects, but we're studying their total collective glow, something called the extragalactic background light. And that, like the microwave background, is an accumulation of all the light that's emitted over cosmic history. And it piles up into this background glow. And it contains the emission from everything. First galaxies and stars that turned on, they emitted photons. Those photons are captured in the background light. The history of galaxy formation, that also emits all those photons pile up into this relic of the extragalactic background light. So what we're doing is we're studying this total glow. And the way this works, you might say, why don't you just measure the total brightness of the sky? And this picture shows why that's challenging. And the reason is our sky from Earth is not perfectly dark. There's two components here that you can see. One is the plane of the galaxy, which is over here. So all those stars create a local foreground that obscures the extragalactic light. But the big one is this stuff. And that's actually something called the zodiacal light. And not a lot of people have seen it these days in the bright skies that we live in. But this zodiacal light is created by basically scattered sunlight. This is dust in our solar system that's scattering light in the optical from our sun. It also emits thermally. It's about the same temperature of the Earth as observed from the Earth. And so it also has a thermal component. And it's really bright, and it's hard to disentangle. And I have to say, I have tried from personal experience. But this zodiacal light, as it's called, has one nice property, which is that spatially it's very, very smooth. And so we can use this to get at the extragalactic background light. So here's a picture that gives you an idea how this is done. This is actually real data at longer wavelengths from an observatory called Herschel. And Herschel was a very big telescope, over 3 meters, but at these long wavelengths, the resolution of Herschel is not amazing. And so you can see all these dots in the image. And for the most part, if you point to a dot, you can't be sure that it's a single galaxy or 2 or 3. Okay, so it's not so great for pulling out individual objects. But if you squint and look at this image, you can see that there's a pattern. The galaxies are clustering together. And that's because galaxies are not distributed randomly. They follow the underlying matter in the universe, something called dark matter. And so we can use this as a way to measure the light from the galaxies. So this measurement actually with Herschel was beautiful. Like we see the structures that we expected. The main issue was that all the light over cosmic history just piles up into a single band. So it's hard with a few measurements to untangle that history and say when the light was produced and at what time. So this is a little illustration to show how this process works. So what you see here is a numerical calculation of the formation of dark matter, which is then traced out by galaxies. And if I used a large telescope and pick out the individual galaxies, I would tend to observe the brightest ones. And then I would have a data set that looks like those galaxies. And I could study them in more detail, and they're very interesting and so forth. But they're not really telling me the whole picture. Instead, who needs the individual galaxies? Let's just look at the structure in the map. And so that structure is actually reflecting the emission of everything, all galaxies. And so it's actually quite different and quite powerful compared to counting the galaxies one at a time. But the key, as I mentioned, is really spectroscopy. If we want to understand the history, we can't just look at a band or two. We want to get enough information so that we can untangle that cosmic history. And so that's where the SPHEREx comes in. We're going to have multiple bands out here in the infrared, and each of those bands is seeing a different history through the cosmos. So their sensitivity to cosmic history is different. And so we can use that information to do an untangling. And again, this method is interesting because we're measuring the emission from everything. We measure the emission from all the galaxies, whether they're dwarf galaxies or strip stars around the peripheries of galaxies, or even exotic things like dark matter decay. As long as this emission source follows the underlying dark matter, as long as it feels the force of gravity, we're sensitive to it. So this will be very interesting when we complete these measurements to compare with what we think we know from our measurements using individual galaxies. And then thirdly, how did the universe begin? So again, this is going back to that picture that I showed, the cartoon history of the universe. 13.8 billion years of cosmic history with the universe starting in a hot Big Bang. Now that picture of the hot Big Bang has been in place since around the 1920s. But in the 1980s, there was an addition, and that's this very early epoch called inflation. And why do we have inflation? So inflation explains some of the fundamental properties of the universe that would otherwise be hard to understand. One of them is the uniformity of the universe. And what I mean by that, this picture of the microwave background here, this has actually got a big offset removed. These are the structures, and you're zooming in on the contrast of that image to show the cosmic structures in the microwave background. But what you don't see is that the temperature of the background is incredibly uniform. It's uniform to like 10 parts per million. So in other words, when I look at the entire sky, and I have photons coming from this direction and this direction, they look the same to 10 parts per million. And those photons have just gotten to me. So in this traditional picture of a hot Big Bang, without inflation, these regions of sky are completely independent. They've never been causally connected. Their photons are just reaching me. They haven't had time to communicate and say, hey, my temperature over here, it's this. So how do they all know to have the exact same temperature? So this is a mystery that inflation solved. Another mystery that it solved is, why is the universe geometrically flat? In other words, if I draw a big triangle in the universe, the angles of that triangle add up to 180 degrees, just like in Euclidean geometry. When inflation was proposed in the 80s, we didn't know the universe was flat to within a factor of 10, okay? But for theorists, that was enough, because you would have to finely tune the early universe to ridiculous precision to get the level of flatness we see today. Okay, so inflation solves those problems, and I'll explain more about how that happens. But, what caused it, if inflation is the right theory? And so with SPHEREx, we're doing a measurement to try and understand the process of inflation, if inflation's the right theory. Okay, this is a picture from Alan Guth's book on inflation. So he was one of the pioneers of inflation in the 80s. And so basically the idea with inflation is, prior to inflation, prior to this expansion, the entire observable universe was smaller than an atom. Okay. And then inflation somehow caused the universe to greatly expand. And it did that by expanding basically space faster than the speed of light. Okay. And you can do this in Einstein's equations as long as you have a substance with a particular equation of state. And if you have a substance that does this with a negative pressure, so-called, we don't know of any materials that do this, but that can give you this superluminal expansion. And so then the observable universe prior to inflation is all in causal contact. Inflation happens, it flings that observable universe out to enormous extents, and in the process of doing that, all those regions that were causally connected are then flung out to these large distances. So that explains the uniformity of the microwave background, because all those regions were, prior to inflation, in causal contact. It also explains the flatness of the universe, as you can imagine. Imagine any geometry and then expand it tremendously. It's going to look locally very flat. Now, I have to say I love this graph. I showed it many times. It's really a physicist graph. You can see that there's 50 orders of magnitude here on the x-axis and 100 orders of magnitude on the y-axis. All this cool stuff here happens when the universe is of order a trillionth of a trillionth of a billionth of a second old. And, oh, by the way, the universe that we can observe is all behind this red line. Everything we know today, the oldest photons in the universe, basically get us to this red line. So how can we learn more about inflation? Another thing is, we don't know how to get this equation of state, but it probably involves exotic physics at high energies. We think the energy scale of inflation is something like 10 to the 16 giga-electron volts. And if that unit isn't very meaningful to you, the energy of a proton is about 1 giga-electron volt. And the most capable machines to study high-energy physics get to about 13,000 giga-electron volts. So this period of time is also quite inaccessible to these particle experiments on Earth. So if we want to learn more about inflation, really the universe may be our best laboratory. So these basic predictions of inflation have actually been validated. Through decades of measurements of the microwave background, we see many predicted signatures of inflation. There's about 6 different tests, and they all just check right off. So we have to start taking this theory seriously. Also, these lumps and bumps you see in the microwave background, that tells you the geometry of the universe, because you think you know their size. It's like a giant triangle. And now we know the universe is flat to better than 1%. So, boy, the inflation is really doing a good job there. So how do we learn more about this theory, given all these constraints? One way is to study the polarization of the microwave background, because what inflation does is it blows up the universe from a subatomic size. At that size scale, quantum mechanics is important. So there's fluctuations from quantum mechanics that are amplified tremendously by inflation. So one of the mind-blowing things, many mind-blowing things about inflation is that all the structures we see in the universe were born from quantum noise. We are born from quantum noise. And maybe gravity is also quantized. So if there's a quantization of gravity, that would lead to a background of gravitational waves, which then we could see in polarization. So that's one test. The other test is let's look at the brightness distribution of the microwave background. So in other words, I can take this map and I can ask, what does its brightnesses look like? What are its statistics? And if you do that, you can make a plot and it looks exactly Gaussian. That itself is pretty cool, right? There aren't too many things in nature or in astrophysics where you can do that and see something that's really exactly Gaussian. And that's another basic prediction of inflation. Then the question is, if we want to learn more, maybe, depending on the model, there's some deviation. And so if we had enough sensitivity, that would look like some tail in the distribution. So this has been done. It's been done by, most recently, the Planck satellite, which did an exquisite measurement of the microwave background. And the answer is there's no detection of non-Gaussianity. And even worse, it's very close to fundamental limits. It's limited basically by cosmic noise. And that's basically due to the fact that there's only so much independent sky that we can see with this 2-dimensional picture of the microwave background. But those quantum fluctuations from inflation, they source the hot spots and cold spots here in the microwave background, but they go on to seed the large-scale structure. So the hot spots are overdensities, and that's preferentially where dark matter is formed and then where galaxies form. And the cold spots are underdensities. So the structure that you see here is reflected in what comes later, which is the large-scale distribution of galaxies. So with SPHEREx, the idea is we want to study that 3-dimensional structure because it's actually much more powerful. There's much more information in this three-dimensional view than in the 2-dimensional view. And in fact, we can do about a factor of 10 better job than what we did before here. So how do we do that? So this movie indicates, this is a numerical simulation. It's a simulation on a pretty big cosmic volume, about 500 million light years today by 440 million light years. And up in the upper corner, you can see time evolving. Okay, so this is basically driven by gravity. And what you see here on these large scales is this characteristic webby structure. But as the clock is going on here, you can also see that there's a lot of complexity happening. On these small scales, now we're starting to see these galaxies interact. They're starting to orbit each other. And gravity is a nonlinear force. So it's getting pretty complicated if you're a physicist and you look at structures on small scales. But on large scales, this picture really didn't change from the beginning. It got accentuated, but the imprints that we had were there right from the beginning. And so that's kind of the idea here. The imprints from inflation, if we go and we look on big enough scales, the imprints are there in the structure of galaxies. We just need to look on large scales. And the reason is that there's only so much time in cosmic history. 14 billion years, yeah, that's a lot. But there isn't time for galaxies that are far separated to really feel the effects of gravity from each other. So in order to explore this, what we want to do is we want to build this three-dimensional picture of galaxies. And so that's where SPHEREx comes in. We're a galaxy redshift machine. And the idea is, with our low-resolution spectroscopy, we can rapidly get the distance, basically, to these galaxies where we know their positions. So here's an example of doing that. And it's a combination of using continuum features in the galaxy. You have that basic template, and you can shift it around to determine the distance, because redshift is basically stretching the wavelengths. So you can fit that stretch from the measured spectrum. And in some cases, we have galaxies with prominent emission lines, and that gives us a really super accurate measurement of the observed wavelengths and tell us directly the redshift. And so we get this distribution of redshifts. They go out to high redshifts or way back in time. And accuracy tends to get worse as we get further out. But this survey is important in the sense that we have a continuous measurement over cosmic history, and it's covering an enormous volume. We're doing this over the whole sky, and we're also doing it in the infrared, where local contamination, like the plane of the galaxy, is reduced. Okay, so that's the idea with SPHEREx. And then when we compare this, there's other surveys, so I'll just mention a couple. This is another way of looking at the universe. So what I'm plotting is the universe as a function of age. If you look back in time, what that looks like. So locally, we see the Earth here, and this is that webby structure of galaxies. And as you go further back in time, at some point there's the galaxies turn off. They don't happen anymore. And this outer shell is the microwave background. And what you see here is redshift. Okay. So we want to map out a large cosmic volume. And here's some examples of similar experiments. There's a survey called Euclid, which is a space European cosmology machine. And it's looking for the properties of dark energy. And with dark energy, at the time Euclid was designed, it looked like the most interesting epoch is around here between redshifts 1 and 2. So they focus on that period of time to see the influence of dark energy. They're really a dark energy machine. A coming observatory is Roman, and Roman is still deciding how exactly it's going to do its survey. In some of the initial designs to complement Euclid, it's going very narrowly. But to study the properties of inflation, we really want to cover the whole sky and cover the redshifts uniformly. So SPHEREx fits in the middle here. We cover the entire sky, and we do it all spectroscopically, starting with high accuracy ones at lower redshifts and gradually having less and less accurate samples, but doing the entire sky. So SPHEREx is really optimized for this inflation science. And so basically what you can see is, depending on the model of inflation, we can get these statistical effects. So here's 2 cases of inflation. There are many, many models of inflation, many models, but they can be broadly classified. And so one classification is whether it's driven by a single field or multiple fields, and there are observables that come with this. So in single field inflation, that is amplifying this base quantum noise, and it produces structures, but without detectable non-Gaussianity. Whereas if inflation is more complicated, it has multiple fields that interact, it can produce more complex structure. And so you can see more overdensities and more underdensities in this scenario. So by pushing the measurement technique to much better precision, this giant three-dimensional map of galaxies will help us determine which of these two scenarios is correct. And then, in the midst of all this, we'll also get this great all-sky spectral survey. It's the first of its kind. There have been many all-sky surveys, but this is the first one where every pixel on the sky is going to have an infrared spectrum, albeit at low resolution, that comes along with it. And so the sky is very rich and interesting, and so this data set is going to be very rich and interesting. Hundreds of millions of galaxies and stars, even things like the spectra of comets and asteroids, who K.C. Liss is working on, line emission from our galaxy, and unusual objects like emissions from very early supermassive black holes in the cores of galaxies. And so in order to facilitate the exploitation of this all-sky survey, we're going to be putting the data out in rapid fashion. Basically, our data rolls off the conveyor belt 2 months after it's observed and builds up a catalog that astronomers can go off and exploit. Okay, so I wanted to move on. That's our science case, but I wanted to tell you a little bit about our preparations for the launch, which consumed the last, I guess, 2 months, and then now that we've been in orbit, check out the remaining 6 weeks of my life. This is a picture from mid-January. So for the last year, prior to this, our instrument was integrated with the spacecraft to make what we call an observatory. And that observatory was located in Boulder, Colorado, with our industrial partner, British Aerospace Systems. In mid-January, the observatory was transported by truck across the western US out here to the Western Range, and this is the Vandenberg launch site on the central coast of California. This is the observatory, and the transportation is quite an involved process. There was a truck that went in front with a pole to make sure that the bridges were indeed low, as expected, across the state lines, and was continuously purged here with dry nitrogen. So this is its storied arrival at Vandenberg. At about the same time, there was a launch at Vandenberg, and as you know, a SpaceX launch, they recovered their boosters, and this was our booster. So about the time we arrived, our booster landed and was refurbished and then reflown on our flight. Pretty amazing. Okay, here's SPHEREx now at Astrotech, ready for integration with the payload. And again, you can see these very distinctive cones. And then this is the spacecraft that was provided by BAE. It's a very agile spacecraft, so it slews and settles and points very accurately. At this stage, the next step is to then integrate SPHEREx with the adapter so that it can mount onto the vehicle. Some time passed, and we had many launch delays, which were frustrating, but this is the final product. At the top here, you see SPHEREx with these cone shapes again, the spacecraft. This black thing is a payload adapter to this ring here, and this is a standard ring, and on it are 4 small spacecraft. So we were co-launched with a heliophysics small explorer called Punch, and these boxes that you see here, here, and here are 3 of the 4 Punch spacecraft. And then finally, there's another adapter below. The surround here is actually the insides of the fairing, okay? And this fairing is enormous, and you can't quite tell from the picture here, but we're barely filling up half of it, okay? So, you know, the space flight community has made just incredible strides in the past couple decades. Okay, so we did this fairing integration. This shows a quick movie of that process happening. The fairing is actually about 40 feet tall. And we loved doing that integration so much, we actually did it twice. Long story. So as I mentioned, there were many launch delays. And this is a picture of the graduate student office at Caltech placing bets on when the launch is going to be. And so those graduate students are pretty good. You can see the predictions. The red line was made on the 3rd of March, predicting a launch on the 10th of March. And they would have been right, except for the fact that that Monday was not good weather day. So we actually launched the day after. So pretty good, go grad students. Meanwhile, our team was in Lompoc, California, which actually is a delightful area. And we diverted ourselves with many activities, including a mural gallery, a train station that's on the beach, and then skydiving. Some of the, not me, some of the postdocs went off and did that. And you can actually see the green circle is our launch site with the vehicle sitting out there. I went wine tasting. But finally, we were ready for launch. And so you can see this is the assembled vehicle with the sun setting. We launched just after sunset in this beautiful setting at Vandenberg. This is the assembled team that was out there, what was left of it, after these delays. And you can see the vehicle in the background. The pad we're on is actually the landing pad for the booster. And people in the red shirts are on SPHEREx, and the blue shirts are Punch. And people without shirts are either from NASA or SpaceX. Obviously not the full SpaceX group. One thing I want to say is one of the keys here is superheroes. And I'm not kidding. So these are actually some of those superheroes from Caltech. You can see these are young scientists. And we actually tested the integrated instrument at Caltech. And one of the reasons for doing that is that these people are actually experts. They have built purpose-built cosmology instruments, from beginning to end. And they've seen that whole process, which is unique and different from aerospace engineers at JPL. And while we were developing and testing SPHEREx, we have this combination of people who've built instruments and used them and analyzed the data and, suffered in the process. And aerospace engineers who are coming from the other direction, they know all the engineering, but they don't know the specific requirements of this kind of very specialized instrument. And so having the two work together was really great. And we worked in this, amazing badgeless environment where we had people at JPL working with people at Caltech every day, very smoothly and congenially. So this is the video of the launch. I hope the sound works. There we go.
SPHEREx, go Punch.
SPHEREx and Punch on their way to map out our universe like never before and revolutionize space weather forecasting.
Stage separation confirmed.
And back ignition.
Stage 1 boost back startup. Coming up next, we will see fairing deploy, and that's when the two fairing halves will separate and expose SPHEREx and Punch to the atmosphere of space.
Fairing separation confirmed.
In about 30 seconds, we will have payload deploy of SPHEREx.
SPHEREx separation confirmed.
SPHEREx is drifting away from Falcon 9's second stage, confirming deployment. The mission isn't over yet. Falcon 9's second stage is still carrying NASA's Punch mission.
Separation confirmed.
Wow, look at that. To actually see them, that's great.
Okay. Some funny things happened on the way to low Earth orbit. Just recount. So you saw that separation video, and we worried about many off-nominal cases. What happens if it tipped 2 sigma to the left? What if it tipped to the right? And what we didn't anticipate, it was actually perfect. And the result was that the spacecraft was in the shadow of the vehicle for over 3 minutes. And so that confused our spacecraft because it's designed to find the sun and it's in the shadow. So, but once it got out of the shadow, it found the sun and acquired a safe orientation. The other thing was that we were supposed to get a downlink over first Antarctica. That video came from Antarctica, but our data did not. And maybe it was a good thing, because we would have been wondering what the spacecraft was doing. And then as we're going around the Earth, we go over our next ground station, which is Svalbard in the Arctic. And for other reasons, we didn't have any communication with Svalbard for several minutes. So it's sort of a Apollo 13 moment there. And this is a video of the science team reacting, trying to figure out what to do when the next ground station pass will happen. And they're at the launch center here at Vandenberg, kind of sequestered off to their own room. So maybe you can hear them or turn up the volume a bit.
Let me check what's the next path after this.
45 minutes, right?
Data. Meanwhile, all of us bigwigs are in this communication room not knowing what's going on.
They don't know that yet. They don't know that yet. They don't know that yet. They don't know.
There was a bit of a delay there. But we didn't have sound from them, and I wasn't looking at my computer, but yeah, we figured it out. So yeah, then we saw the spacecraft. So that was on March 11th, and then one of the first things we had to do was cool down the instrument, okay? And we did this in a special way. We want to get all the water off the instrument because we're trying to detect water ice, for crying out loud. So in the early stages of the orbit, we're using the Earth as basically heating and cooling to drive water off. And so this sine wave you see at the beginning is from that process. And then we ejected our lid and let the instrument cool down. And eventually here, after a period of a couple weeks, we got the telescope to 62 Kelvin and the detectors to 45, and they're actually controlled to 20 microkelvin. So it's working great. After popping off the lid, we have our first light image. And so this is what the sky looks like with SPHEREx. And the bands you see are our 6 bands. So this is the shortest band going out to the longest band out here. Key is the size of the full moon. So this just shows like the enormous field of view, the amount of light we're gathering in these exposures. So this is 1 2-minute exposure. You can also see some other stuff, and one of them is this thing. That was a little bit unexpected. We did expect to see it, but not at this brightness. And this is line emission from helium in the Earth's upper atmosphere. And so it's brighter at this time, also because the sun was going through a period of peak activity. This stuff at the bottom is that line again in the overlapping band. But we see the telescopes in focus, and things are really working great. And actually, there's a ton of information in these images. If you zoom in, you can see actually there's a pair of nearby galaxies. And then the point spread function of the telescope is excellent. So we can see we're in focus. So that was a big moment of relief. I like this because it's showing really how we do the observations. So that's that first image, but these things are just coming down every 2 minutes. And so over the day, course of the day, we get 600 exposures or 3,600 images a day. So it's just a fire hose of data that's now upon us. Here's just some gratuitous views. So most of the time, we're actually trying to do engineering, okay? And then we come across images like this and go, oh, well, that's cool. And so what you see here is a region of the galactic plane. On the left side, it's at the short band, and on the right side, it's at the longer band. And at shorter band, the effect of dust in the galaxies exacerbated. You can't see through the dust as well at short wavelengths as you can at long. And so here at short wavelengths, we see dark lanes and stuff associated with dust. We also see a lot of reflection off of dust. This bright stuff is starlight that's scattered off of that foreground dust. But as we go to longer wavelengths, kind of a magical thing happens. We start to see through that dust in the galaxy, And this is the same region to reveal the stars behind in the plane of the galaxy and in the bulge. And quite a different view. You can also see there's still some thicker dust out here, and I'll talk about that in a bit. This feature is actually line emission from hydrogen. So a nice gratuitous picture, just, one of the things we're seeing pretty much every day. And now the real strength of SPHEREx is to do its spectroscopy. And in order to do that, we have to build up images at all these wavelengths. And that takes a while, a few weeks in a given region. So at this stage, we're just starting to put that puzzle together. And so what I'll show you here is a sequence of observations taken at multiple wavelengths, but it's not a complete picture. So this is the region of the galaxy that we're looking at. And I'm going to step through the wavelengths. So the first thing you see again is at the short wavelengths here, this dust, and at the long wavelengths, you're seeing the stars behind the dust. And as I go to the next picture, I think you can see that these clouds here are getting darker, which is kind of surprising. As you go to longer wavelengths, you'd expect them to be more transparent. And that is what we think is the effect of water ice right off the bat. And that's pretty exciting. It took us a while to convince ourselves this was actually the effect, but we're seeing this absorption in bulk clouds just because of the background stars hiding behind those clouds. And that feature is pretty broad, so you see it. And now something else is happening. You can see these regions start to light up. And especially if you look here on the right, these regions are suddenly flaring up and getting bright. And so that's another effect. And this is called from polycyclic aromatic hydrocarbons. So these are large organic molecules in interstellar space, and they have these characteristic emission features. And so we're just seeing those, they're almost like proto dust grains, like before they form. And we're seeing these features light up everywhere. And then as we go on here, these are the two more bands. Here again, we're at short wavelengths. So you have a much different picture here at long wavelengths. And now as we go along, we see that hydrogen emission line that I mentioned. And as I step along, boom, something interesting happens. This is a molecular hydrogen line. So it's a molecule. And it's forming this pattern, which is from an ancient supernova remnant. And that was a topic of like why, could this feature be explained by molecular hydrogen? We just see that coming out of the data. And then one more thing here, as you look, these clouds here suddenly become much darker again. And that's that much sharper feature from carbon dioxide ice. Okay, so that's just a peek. Trust me, there's a lot more of data available that we're still going through. But our next step is really to start our scientific observations. And we're in a place now where those scientific observations will start, we hope, in about a week. And we have a happy spacecraft, the instrument's working well, and it's a very exciting time, and we're looking forward to now starting our science phase. So with that, I'm happy to take questions, and thank you for listening.
So, as many of you know, we have a procedure for questions. We'll start with the blue mic.
Mike Albro, and I'm a member. Thank you very much. It's so interesting. You said there are 100 bands in which you look. Could you explain a little bit about the technology for separating these bands? How is that done?
Sure. So the method, as I mentioned, was basically to put a filter on top of the detector. So these are interference filters. They have multiple layers of coatings that make the filter basically resonate at a particular wavelength. The difference from a conventional interference filter is that the coatings are shaped so that as you go from one edge to the filter to the other, the central wavelength changes in a controlled manner. So it's called a linear variable filter.
Thank you.
Go to the red microphone, count to 3, and then tell us your name if you're a member and ask a question.
Yes, my name is Frederica Dorima, and I'm a member. Thank you for this very exciting work that you are doing and the presentation. You talked about quantum gravity and what kind of measurements we are going to use and how they interfere, in a sense, or interact with the methods that you developed here.
Right. So there's it's hard to constrain inflation. There aren't that many observables. And so as I mentioned, there's this structure that we're doing with SPHEREx. The other channel is to look for a polarization signal in the microwave background. But what that is caused by is a cosmological background of gravitational waves. So those gravitational waves would have been produced from the period of inflation, much like the structures were produced from quantum noise.
Timothy Thomas. I am a member of the Society. I'm wondering about the formation of galaxies and your SPHEREx. I understand that it's an open question whether the galaxies formed around the black holes or whether the galaxies collapsed and formed a black hole. Will SPHEREx be able to shed any light on this question?
Right. So what we will mostly, what we're looking for is a signature from this period when galaxies formed and ionized the surrounding medium, okay? They can do that with bright stars. They could do it with accreting black holes. And what we're looking for are characteristic signatures from the surrounding hydrogen. So there's like emission lines and cutoff features that distinguish this period from the later periods when galaxies are forming, stars are forming in galaxies, after the universe is ionized. So that's what we're looking for. It doesn't directly tell us the source of ionizing emission, whether it's coming from black holes or coming from stars. So that will be something that you need to investigate the individual galaxies to do.
Ciprian Ivanov, member. Do you expect to detect more space dust than previous models did? And if so, do you expect that to force a reevaluation of various physics models?
So you're asking about space dust, or? So I think, I'm not quite sure I understand the question. We see dust that's mostly in our galaxy. And so the structures you've seen are largely from that. We have to look through it to do our cosmological survey. And then, of course, the individual galaxies that we're looking at are also, to some degree, dust obscured. So I'm not sure if that answers your question, however.
I think it's related to missing mass. So if we're not seeing all the dust, will SpaceX allow us to see dust that we're not presently detecting? And would that have any bearing on what's our estimation of dark matter? I think that's the question.
Oh, so you're interested in dark matter. Well, we think that most of that dark matter is not conventional matter, not baryonic matter, and dust is made out of baryonic matter. The reason is that early period in the evolution of the universe cooks up some of the light elements, and so that constrains the amount of baryonic matter. And when we look at the influence of matter over the universe writ large, it's much bigger. So there's some additional component of matter that completely dominates over the baryonic matter. It's possible we'll learn something from SPHEREx, and so as I mentioned, this is a fairly exotic possibility, but in our galaxy formation survey, there might be signatures from dark matter decay that we would see. And there have been papers written about this, saying that this might be an interesting thing to do. It's definitely a long shot, but perhaps that would tell us something about dark matter.
I'll go to the blue microphone, and then Jennifer, I think you have a question.
Yeah, Mark Coles, I'm a member. Is it possible to make at least some of the measurements ground-based? I mean, for instance, could you do it in the South Pole during the Antarctic winter?
Right. So I should say that there's several reasons it's really hard to do these measurements from the ground. For the cosmology survey, we really want to have fidelity on large angular scales, like 30-degree scales. And so that's really hard to do from the ground just because of the atmosphere and weather. There are ground-based cosmology surveys engaged and active. In fact, there was a recent result from this DESI large-scale structure survey, which looks very interesting. But to get out to these large angular scales is definitely a challenge from the ground. It's also very hard to do these mapping measurements from the ground, as you can imagine, with a variable atmosphere.
We're going to go to Jennifer with the red microphone, but first, we're going to take a couple of questions from the YouTube viewers.
Our first question comes from Michael Haken in Silver Spring, who is a member. Can SPHEREx measure the abundance of H2O in the Kuiper belt, and can it distinguish between amorphous and crystalline ice?
Right. So there is a component of ice in our solar system. We'll be looking for that in bodies like asteroids and comets, not so much Kuiper belts objects, because that feature may be there in the ice, but something has to light it up, either reflected sunlight or something behind it. So it's really hard to do that with Kuiper belt objects. But in our own solar system, it's an interesting question to look at the mineralogy and ice abundance in asteroids and other bodies in our solar system, as Casey here can tell you.
And our second question is from Eric in Sweden, who is not a member, and it ties into a question that Michael also had. How many asteroids are you expecting to discover with SPHEREx? And can you determine abundances relative to other volatiles?
Yes, so we have engaged in a solar system objects catalog. Casey here, a member of PSW, is the leader of this endeavor, and the catalog is curated by our Korean collaborators. We are starting out with doing spectra of known objects. So basically, these are moving objects, you know their position, and then we can do photometry and look at their spectrum. And that spectrum tells you the mineralogy of the asteroid, as well as it can pull out, the abundance of perhaps the existence of ices. The particular chemistry of water ice is actually really complex, and so it's an open question exactly what that spectral shape would look like, because this is not my field, but it changes as it's intermixed with other materials.
Cool. Thank you.
Red microphone.
Jennifer Wiseman, I'm a member. And my question to you is about the data. You mentioned something about it at the beginning of your talk, but this looks like a wonderful treasury of information, this all-sky survey that will likely be useful for other kinds of science questions that we haven't even thought of yet. So how are you archiving this data, and how are scientists able to access it, and when, and how are you facilitating that is my question.
Okay, so our repository there's a center in Pasadena called IPAC, Infrared Processing and Analysis Center. So they're doing this initial processing of the data, and then they curate it through an organization called URSA to make it available to the general public. As I mentioned, the images that come off are calibrated and made available to the public within 2 months of data acquisition, and so they're basically coming out continuously. In addition, we provide some tools to do particular kinds of measurements. So if you have 100,000 favorite objects, say, you can feed those in, and then we go through this tool. We'll go through the encyclopedia of obtained images and then find photometry on all those positions and spit back the measured photometry. More exotic tools could be developed, but we're pretty cost constrained, and we expect that the community itself may come up with additional tools beyond what we would provide.
Could we get the red microphone over here? Yeah, thanks, Floyd. And then we'll go to the blue microphone, but I'm going to interject a question of my own, which is, how much data are you collecting in bytes, and how long is it taking to download a day's trove, say?
Okay, so I can put it in pixels, if that's helpful. Each of the...
What bit depth are your pixels?
Well, we have 24 million pixels, so each of those images is about 4K by 4K. 2K by 2K are 4 million pixels, and there's 6 arrays. We get 3,600 individual exposures in a day, roughly. Images, 600 exposures. That data is telemetered down several times a day in fairly brief passes over ground stations. Each of these passes is, several minutes in duration. And with 4 or 5 of those per day, we get down the daily data like that. But it's quite a fire hose.
And where are you storing it?
So the data eventually makes its way to IPAC, and that's where the data is initially stored. And as I said, they do the initial
IPAC
image processing.
What is that acronym?
Infrared Processing and Analysis Center. Yeah.
Yes, which is a. Okay, I'll ask you later. Let's go to the red microphone here.
Hi, I'm Paulos, A.M. Paulos, member. My question involves the collection technology. By looking at your pictures, I see that you have, looks like you take 3 different passes with 2 different banks of CCDs that are probably adjacent or on the same substrate. My question involves the filtering technology. Is it a mechanical filter that you switch out every 2 minutes, or is it some type of electromagnetic filter that I'm thinking about the power constraints, and I'm an engineer. So.
Yeah. So the filter, as I said, is this piece of sapphire that goes over the detector. And so it doesn't have any power that it's dissipated. There are no moving parts. So very, very simple method. And the way you control the wavelength range is to shape the progression of layers to have the desired wavelength progression. There's a company in California that makes these, and they did a really exquisite job nailing that progression and controlling leaks and so forth.
Blue microphone.
I'm Bob Hershey. I'm a member. When observation starts in a week, what will be the first things you'll be looking at?
So we survey the whole sky. So basically our target's the whole sky, and we just start our survey. And we survey whatever strips happens on, that start of survey day, and start observing our 360 degrees great circle. So there's no preferred region. But I should say that as we're doing these observations, we're always crossing near the Earth's poles, or the ecliptic poles, which are 90 degrees from the sun. And so we use that effect to actually go much deeper in those regions. There are about 50 times more observations there than on a given place on the sky. And so those deep regions are ideal for doing this mapping measurement for the extragalactic background light.
The red microphone, Casey.
So I'm Casey Liss. I'm a member, also a member of SPHEREx. So I'm going to give you a chance to crow. You talked about in the CMBR maps taken by Planck and WMAP that you needed to get down to a few parts per million to see the structure. So you also showed the structure you expect from SPHEREx. How much of that foreground light of everything, the planets and the brown dwarfs and the stars and the Zodi, do you have to remove? Are we also going to have to get down to ppm level and in looking for the signal from the cosmological signal?
Yeah, so I think you're referring to the intensity mapping measurement.
Yes.
Where we're doing these multi-band maps. And so we're looking for a structure that's very, would seem to be faint, and it's underneath these foregrounds. Right. But it's not as bad as the microwave background, because the total amplitude we think is maybe, the fluctuations are actually bigger than the emission from the zodiacal light. They're fainter, but the zodiacal light, we're using the fact that it's very smooth to do that. So we're not digging down like orders of magnitude into this signal, at least initially. But like a component from reionization, that's going to be buried under all that other galaxy formation history that happened since. And so one of the challenges we have is to pull that out. We need to know the history of galaxy formation, its emission, to model that, to dig out this early signal.
And how long do you think that might take?
Well, this is very exploratory because nobody has measured it. So it may take a while, but I think there are a number of methods that we can use to dig it out. So one of the powerful methods here is we can actually take galaxies where we know their distances, that we know their redshifts, and we can just use that pattern and cross-correlate it with our maps. And that actually just pulls out emission from that particular slice. And we can do that slice by slice as long as we have galaxies. So a lot of that emission we'll just measure in that very direct method.
Now I think we're at the blue microphone.
Pramukta Rao, a new member. I was wondering whether your map will have enough resolution, or the combination of your map and sensor would have enough resolution for something like that to relocalize itself based on your map. In other words, provide possibly a more resilient way for satellites to determine their location in orbit. In place of a star tracker or something like that.
Right. So the way we determine our pointing instantaneously is there are systems on the spacecraft. There's star trackers, which give us the absolute position, those two horns. You're right, those are star trackers. And then there's inertial pointing systems that control the stability and also interleave between the star tracker pointings. But our images are actually, as you say, quite helpful for determining the absolute pointing. So yes, we have already done that, just using the position of all the stars, and we can do that to a small fraction of a pixel, in fact.
And sorry if I could follow up. So would your sensor system be a sort of a cost-effective way for a I mean, obviously not with all the fancy components on it, but the general strategy be suitable for like a
Speak into the mic, please.
Oh, sorry, a small planet dove or something of that nature. Some sort of like CubeSat or something also.
Yeah, potentially there could be other applications to. You basically use the subpixel location of the stars. It's not the way normally people build a star tracker, but you can centroid all the stars and they're the bright stars, and then kind of fit the template to really get a precise alignment. Yeah.
Red microphone.
Yes, Eric Wargot's a member. Two questions. I think they're rather elementary. They should be easy for you. How long is the mission scheduled for? How many years? And number two is I'm more interested in learning about it. I understand one of the big challenges with this technology and what's being used is maintaining the low temperature, the extremely low temperatures. And I'm interested in learning how you've addressed that issue and how you reach equilibrium on that, how you maintain that. If you can briefly discuss how that's managed, because as we all know, the instrumentation won't function above these extremely low temperatures very well, and will introduce a lot of distortion and errors. Thank you.
So what was the first question again? Oh, the duration of the mission. Yeah, easy one. I've already forgotten. So the baseline mission is 2 years of observing, but we have no consumables. There's no cryogens. We run off of sunlight. There's no propulsion. So there's nothing except for eventually the decay of the orbit that sets the mission life. The orbit's good for of order 20 years. But our baseline is 2 years, and then we would have to get renewed at that point. In terms of the temperature stability, we have precision temperature readouts and control heaters on the detectors. So they're controlled from this precision thermometry, and there's enough thermal reserve, so that we can elevate and control at a specific temperature. And as the base temperature might change a bit over the flight, we can always control at our desired temperature above it. If we turned off the heaters, it would actually cool further.
What is the ambient temperature where you are?
I'm not sure. Well, we're in low Earth orbit, so
yeah, no,
the radiative environment's kind of 300 Kelvin. Yeah.
Blue microphone.
Hi, my name is Matthew Zamora. I'm a guest. My question is, and it's a pointed question. I don't know if you're aware, but you had a graphic with the longitude, latitude, and it was showing the ices. And I think you said it was the galactic plane. Is that right? And I was wondering, there was kind of an anomalous blob of ices below the galactic plane. It just almost like an artifact-looking blob. I don't know if you recall that. I was just curious if you knew what that was.
I think this would probably be easier to do offline, and we can go through the images.
Thank you.
Yeah.
Okay. Any more questions? Seeing no questions, let's thank our speaker. We do have some thank yous for you. One is a framed copy of the announcement of your talk. Another is a PSW ribbon emblazoned on the side with the symbol for inductance in memory of our founder, Joseph Henry, who studied induction and inductance, and for who the unit of inductance is named, the
Do
Henry.
the three stripes have some meaning?
Hmm?
Do the three stripes have some?
Yes, it's supposed to be the evocative of the coil that is the symbol for inductance. Right?
Okay.
And the unit of inductance is
So
the Henry. And it's named for the founder of PSW,
Great.
Joseph Henry. And you'll find Joseph Henry's address as the first president in this volume 17, which compiles a lot of histories and the original documents of the organization, articles of incorporation, why the organization was founded, what its purposes are, why it was named Philosophical Society, and a very nice essay on scientific discourse, which we could all stand to read again and again and again, because it basically says you should be free to constructively criticize and receive criticism with an open mind, but not engage in personal attacks. But it's said much more eloquently than that. So with that, thank you very much.
I have some water here.
Before we go, we have the usual closing announcements. Our next speaker on May 9th, he's rescued us from me having to give a talk, which you can imagine would be utterly boring. Now, Casey Liss will be speaking on learning how solar systems form. Now, that is our simplification of his actual title, which will be far more sophisticated, something like observations of the formation of the earliest solar system materials via destructive accretion of migrating asteroids in the sun-like T Tauri RW Auriga system. Something like that. Anyway, it promises to be very interesting and I think fun, because Carrie's got a great sense of humor lecture. And I'm looking forward to it. This is this year's presentation by a PSW member. It's an annual event we initiated last year with talks by 3 PSW members way back in January of last year. The rest of the spring season is listed here. After Casey will be Mark Palmer, who is at Brookhaven, and he'll be speaking about muon colliders. And I will confess that I'm the one who decided we got to invite somebody to talk about muon colliders. Why should we talk about muon colliders? Since they're a figment of imagination of physicists who want to be able to build very powerful colliders without having to convince governments to pony up tens of billions of dollars and engage in tens of years of development. So, but the physics involved in making a muon collider is pretty astonishingly challenging, and it takes a great deal of chutzpah and belief in engineering capabilities that we can develop to make one, because they operate on very, very short time spans, because muons don't last very long. And so anyway, it should be a lot of fun. So I recommend everybody to come and hear that if you like those sort of high energy physics kinds of talks. And then on the 2517th meeting will be on June 13th. And I suppose this, some people might consider this is equally a imaginary technology, but these people are actually building a tokamak right here in Virginia. The lecture will be by Alex Creeley, who is the director of tokamak operations at Commonwealth Fusion Systems, a company that aims to commercialize the production of electricity using fusion reactions. And like I said, they're actually in the process of constructing a tokamak to do just that right here in Virginia. Why should they succeed where ITER has failed? Because the magnets that are available now are an order of magnitude more powerful than the ones that were available when ITER was first planned. They have 20 Tesla strength magnets. Having much stronger magnets means you have a greater ability to confine a plasma. You can build a smaller reactor, which also gives you advantages in terms of the size of the plasma you need to contain, et cetera, et cetera. So we'll see, but it should be a very interesting talk. June 27th will be the 94th annual Joseph Henry Lecture and the 2,518th meeting, and it will be on June 27th. It will also be the last open lecture meeting of the spring lecture series. The speaker will be Jason Dworkin. He is the senior scientist for astrobiology and project scientist for the SPHEREx mission. He will be speaking on analyzing samples of the asteroid Bennu that were brought back to Earth as part of the SPHEREx mission. And it's been in the news lately because of the organic molecules that they detected in those samples. So again, this will be a fun and interesting talk. And then finally, the last meeting of the season will be the annual meeting for members. There will not be a lecture. And this is when we give a presentation on the state of the society and answer questions about where we're going, where we've been. And finally, to begin the fall series, we have on the 2,520th meeting on September 5th, the speaker will be Will Marshall, founder and CEO of Planet. And of course, we'll be speaking about Planet's constellation of Dove small sats that provide daily hyperspectral images of the entire landmass of the Earth. And that should be a very interesting talk, too. Much like Starlink, Planet's imagery has transformed how people look at the dynamics of what's going on the Earth in a way that I don't think people really realized was going to be as impactful as it's been. So that will be a very interesting and fun talk. Finally, let's thank our crew. So with that, I will accept a motion to adjourn the 2,514th meeting to the social hour. Bob's got a motion. Do I have a second? All members in favor? All members opposed? Meeting is adjourned.